Numerical integrations are used to approximate definite integrals and improper integrals. The definite integrals such that the integration for f of x dx runs from a to b, defined value to another defined value, and using the fundamental theorem of calculus that was equal to the capital F of b minus the capital F of a, such that the capital F is the antiderivative of the f, small letter f, inside the integral. The improper integrals where one of the boundaries or one of the limits is infinite. So it may be running from negative infinity to infinity, or from a to infinity, or from negative infinity to b, a certain value. So these two types of integrals are approximated numerically using techniques. Why do we need to do this? Because at many times the evaluating this antiderivative is very difficult. We have a composite function which is not very easy to get its antiderivative. Sometimes it's impossible, or we may not have an f of x from the beginning. We might have only recorded data from a certain lab, and we cannot put it in f of x, or we might use to interpolate it, of course, first, which will run many addition to errors. Like we know that one of the definitions of the definite integral is that the area under the curve. So if we have f of x running from a to b, the integral from a to b for f of x dx is approximated by the area under this curve from a to b, this highlighted area. So we have two techniques or two methodologies, one using equidistant subintervals, dividing this interval from a to b into equidistant subintervals, and other techniques using non-equidistant subintervals. Of course, in the equidistant intervals, we will find that increasing the number n of subintervals will enhance the accuracy of the approximation, while in the non-equidistant intervals, it would consider a completely different thing, which is the curvature of the function itself. So the first technique is the trapezoidal technique, which works on the f of x itself. It approximates it into a linear function. So this curve, blue curve, is approximated into the straight line. We may use this interpolation using any of the techniques previously studied, and then we will approximate the whole operation, the integration for f of x dx from a to b, with the formula h by 2, such that h is the interval b minus a, multiplied by average of the two heights, which is the familiar trapezoid area expression. We might view it from that geometric form, or we might apply the proof using the Lagrange interpolation, interpolating the f of x into a linear ax plus b, and then you will reach the same thing. And this will be denoted by capital T sub 1 for trapezoidal of the simple version. If we worked on the example of e to the power sine x dx from 0 to pi over 2, we will directly apply this formula, which states that h by 2h is b minus a, so it's pi divided 2 by minus 0, pi over 2, multiplied by the sum of the two heights, f of 0 and f of pi over 2. So f of pi over 2, sine pi over 2 is 1, times e to the power of 1, so it's e, plus sine 0 is 0 and e to the power 0 is 1, so it's e plus 1 times 1/2, and this will be the result. If we need to consider dividing this main interval into more sub-intervals, we will be working in the composite version, where the formula or the interval from a to b is divided into smaller sub-intervals, like we see here, from a to x1 and then x1 to x2 and so on. And the formula used at that time, it will be h by 2 multiplied by the sum of f of a plus f of b plus twice the intermediate length. As we see here, f of a is only considered in one trapezoid, right? F of x1, this height is considered in the first trapezoid or subinterval and in the second as well. This is why it's multiplied by 2, all the intermediate heights, up till the end. The last one is considered also once. And this will be denoted by capital T sub n. N stands for the number of subintervals. Here it's 5, so it will be T sub 5. Back to this example, if you are going to solve it using n equals 4, so using here, we will use h divided by 2. H here is b minus a divided by n. So it's the subinterval length. B minus a in that example was by divided by 2 minus 0 by n. Here it's 4. So h is by 4, right? Pi by 8. So you have pi by 2 minus 0 over the 4, which will be pi by 8. So this will be the h multiplied by f of a. So it's f of 0 plus f of b, which is f of by 2, plus 2 times f of 1. 1 will be a plus h. So it's 0 plus pi over 8. And x2 will be a plus 2h. 2h is 2 times pi over 8, which will be pi over 4. So we will have here pi over 2 and then pi over 4 and so on, up till reaching, here it's pi over 8, pi over 4, and so on, up till reaching the pi over 2, which is the last point, or the upper limit boundary. Substituting here in the formula will get us the final result. It's beneficial to apply this in a table such that we have the value x node and its corresponding y node. So you have x node is 0 and its corresponding y node. x1 is pi by 8 and its corresponding f of pi over 8, and so on. Thank you.